in that case, our function is not valid, and that's why we have the limitation that b must be greater than 0. And the second limitation is that b must be greater than 1. This base must be greater than 1. And the reason for that is because if b is equal to 1, then it must either be just below 1 or just above 1 or more, but never 1. And that is because if b is 1, then any number that we raise it to, it can be 1, it can be 2, it can be 4, it can be 100, we'll always get the same answer of 1. And what that means is that our graph will always just be at that position there that I just circled. So we don't want that for this exponential curve. So we'd rather set these conditions and say our function is defined by y equals b to the power x, but b must be, the base b must be greater than 0, and it must never equal 1. Now a quick word, I'm going to go to the back of the chapter, right? To the summary of the chapter. And I just want to summarize something that we were doing with Joy before we thingy it. We concluded the chapter and went into finance, right? And it's about, you know, this thing, functions and trillings. Right, yeah. So a function, are we still together?
Yes.
All right. So I'm just gonna make the next page here on Jamboard. Right, so a function is a rule, and this is grade 9, grade 10 stuff, right? Function is a rule, right? And what does that rule tell us? It tells us that if you have a set of elements called set A and another set of elements called set B, right? So let's say you've got 4 elements in set A and you've got 4 elements in set B, right? And there's a certain relationship between these sets, right? These numbers in each of these sets, right? There's a relationship between the two. Right? Now we don't know what that relationship is expressed by, whether it's y equals mx plus c or whatever, you know what math can be like. But what we do know is that if there is indeed a function between the elements of set A and the elements of set B, if there is indeed a function, then that function is the rule, right? Is the rule that uniquely associates the elements of set A with the elements of set B. So there is a unique relation between the elements of set A and the elements of set B. And each element in set A maps only to one element in set B. I'll repeat that. Each element in set A maps only to one element in set B. And we call this a 1-to-1 mapping, right? We call this a 1-to-1 mapping. Okay. And then the second thing we know about functions, that's the first thing. The second thing we should know about functions, the summary is on page 90. So you can just type 101 on the search thing there, and then you'll find it. It's just this thing is now not refreshing now, so
Yeah, that's why you refresh.
oh, okay. Okay, yeah, now there's everything. Right. So functions can be one-to-one relations or one-to-many, right? So this rule, the function, can be 1-to-1 mapping, or it can be many-to-one mapping. And the reason this is valid is because you can have a straight line, and for every value of x, there is a corresponding value of y, right? Let's make that x1, y1, and we'll just pick an arbitrary point, that's x2, and there's another arbitrary point it corresponds to called y2. So x2, y2, x1, y1. There is always one-on-one mapping for a straight line. So every one x value via this rule is y equals mx plus c in the general cases, right? Via this rule, each x value maps onto one unique y value. And this is called 1-to-1 mapping, right? In a many-to-one type of setting, you can have a simple curve like a parabola, right? So that's y-axis, that's x-axis. So an x value and another x value can both map onto one y value. You see, so this point will be x2, y1, and this point will be x1, y1. You see, so in this case you have a many-to-one. So this is the kind of relationship y equals ax squared, right? And this here is an example of a many-to-one mapping. Yeah, what? Yeah. And then the next important thing about graphs, functions rather, right? When we draw the graph of a function, so let's say we have a straight line function. Let's say we have a straight line function on our xy axis, right? Plus c. And let's say also we've got a quadratic function. We've got a quadratic function y equals ax squared. And we've also got an exponential function, right? X. So now this is y equals b to power x. So in all of these functions, right, there is one simple test that we apply, and that's point 3 on our page 90 summary for functions, right? Okay, let me just switch to this one. Right, so we've got these three functions. These are the primary ones we're going to be looking at in the rest of the chapter. Right, so these functions, we can only determine them with one test, and that test is called a vertical line test. Right. Now, The vertical line test is simple.
Vertical line.
Test, yeah. So vertical line test. Sharp. So now when we have a function, right? A function must pass the vertical line test. In other words, if you see this line, that's dotted line that runs through the x-axis and the curve,
Yeah.
that line, you can slide it to the left of the x-axis or to the right. That line must cut the function, the curve, or the straight line once and only once. If that is the case, then whatever graph you have there is indeed a function. If and only if that vertical line crosses a straight line graph function or the parabolic curve or the exponential curve once. Should the vertical line cross a curve on a set of axes more than once, then that graph, that function is not a function, it's something else. But you will see as we carry on with this chapter that there will be some graphs where the vertical line test is failed unless we specify certain conditions to make that a function that passes the vertical line test. But we will get through that. So vertical line test means vertical line must pass vertical line must pass a graph of function. I'll just call it the graph of the function, right? So the graph of the function, that could be either the straight line, the parabolic curve, or the exponential curve. It must pass graph of function, right? So that's very important. The other thing, once, must pass it once, must pass the graph of the function once, and we'll circle that in red dotted lines, just to show that it's very important that that condition be adhered to. Right, now there's something that we need to also be familiar with. So when we write functions like y equals mx plus c, y equals ax squared, or y equals b to power x, we normally write them in the following format, right? F of x equals mx plus c, f of x equals ax squared, or f of x equals b to power x. And what this just means is a function of x, such that then you read out what's on the other side of the equation. That's typically the language used. I'll just move to the next slide. Yeah, it just simply means, so you can replace the y with f of x, right? And how you read it, you just simply say a function of x such that x equals such that so and so something something something. That one, that's typically how I write it. Now what you will see in the chapter is that we will be able to go from f of x, which is the function, to f inverse of x, which is inverse of function. Right. When you look on your calculator, there is sine, cos, and tan, and they have got sine to power -1, cos to power -1, tan to power -1. You see those notation? Yeah, those are a way of indicating inverses, right? And you will see that when we solve for these, there's a 3-step process that we follow, right? When we represent, and this is just to represent functions. So when we represent functions, you will see that we first start off by replacing. So you don't need to, you can pay very close attention to this for now as I'm speaking, but you don't need to cram everything. And once we finish with this summary, I'm going to jump straight into worked example, and then you'll see, especially this page, how we work with it, right? Especially this part that I'm explaining now. But the first step we do is to swap x and y in the function, and then we make y the subject of formula. And you'll see the techniques we use here are the same as the ones we use in science, and then the same as the ones we've been using before, but a lot of them come from the teachings that we've learned from earlier grades. Subject of formula. And then lastly, we will then express the new equation in function notation. Now, express new function in new equation rather in function notation. Right, so the equation of the formula, we're gonna write it in function notation. So notation, this is the notation here. This here, this is what we call function notation. Alright. So if we represent a function as f, then its inverse is f of f inverse. And that's this part here, right? That's that part there that I'm circling. Now, there's something very important. There's always a discussion that you have to give when you are analyzing functions and their inverses. And this discussion is important because it tells us about how x behaves. In other words, is it a real number? Is it a one, those things from the number systems? Is it an integer? So we have to discuss those things, right? And we discuss them in two places of two. So we have a 2-dimensional plane of existence, right? That we're working with, which is the x and y plane. Now, on the x and y plane, the x-axis represents the domain. So it's a set of x values that make the function, the rule, valid. And we're just going to look at that from the x perspective, from the perspective of the x values. That is in the domain. And in the range, we're going to look at the vertical axis, which gives us the behavior, or the properties rather, of the values that we see in the y-axis that make this function valid. So we'll So we'll discuss that just shortly. And right, domains and ranges. Right, let me just. Is the thing still updating live?
Just wrote
Domains and ranges, yes, domains and ranges, right? So the domain of a function, so let's just use blue ink. I'll just do this because I was doing this with a thing in the summary today. So domain of a function, so you can make yourself a little table like that, right? The domain of a function is the range of that function's inverse, right? And the range of the function, the range, so the ones that have to do with function, I'm writing them in blue. So the range of a function is the domain of that function's inverse. Right, all of this stuff is not making sense at the moment, and I totally understand, but bear with me. They're gonna make sense as we carry on, but just keep them in mind, make a mental note, keep them somewhere where you can easily refer to them, because we're always gonna keep coming back to these slides, right, or to this knowledge, right? The range of the function equals to the domain of the range of the function equals to the domain of the inverse, and the domain of the function is the range of the inverse, right? And then secondly, the inverse, so let's look at straight line, right? Y equals mx plus c. The inverse is also a straight line. For parabolic function, remember when we were discussing when I was just mentioning here, I mentioned that when we were talking about the vertical line test, I mentioned that at some point you have to set conditions so that even though the vertical line test is failed by the inverse of the function, then when we put the conditions, then that which has conditions is indeed a function according to vertical line test. Now this is why I was saying that, right? The inverse of a parabola, so inverse is not a function, is not a function because it fails the vertical line test, right? Not a function. However, limiting the domain can make that inverse of a parabola a function. Right? And then for the exponential function, the inverse is called a logarithmic function. Is a logarithmic function, and we'll see how that looks and how the different rules of manipulating those types of problems, right? And if f of x is b to power x, then f inverse of x is log to base b of x, right? So don't get confused just yet, just pay attention to the terminology, and but but as we get further and further into the chapter, you'll understand where we're going with this. So I just want to finish off with the last. So the log laws we're gonna get into when we're doing the logarithmics. So I'll just leave the laws right here. I'll just have 61 there. Right, worked example 1. So jump straight into worked example 1. On page 48. On page 48. Right? And we are given a function 2y plus x minus 8 equals 0. So we must draw the graph. Draw graph. And determine significant characteristics. So significant characteristics are the things that are important about the graph. And as we solve this, you will understand you might not have to, it's fine if you don't have prior knowledge of graphs. But what I'm going to explain to you is that whatever the significant characteristics of the linear function we have to find for solving this problem, those are the ones that you are taught to learn in grades 11 and 10. And for straight lines, as you will see, these include things like the gradient and y-intercept characteristics, right? So significant characteristics we'll answer in the second part, but for now, we're given our function. It's 2y plus x minus 8 is 0, right? We can write this as a straight line to start with. So step 1, we must write this equation as a straight line equation of the form y equals mx plus c, right? And how are we going to do that? Exactly as we're doing in page 48 of Learning Guide. We're going to go step by step. I'm just going to explain using things like additive inverse so you can see how these things, even though they're from grade 9, 10, and 11, we still use them in our grade 12 to solve for problems. So we start off by saying, let's put additive inverse there. So plus 8 on both sides, so that 2y plus x minus 8 plus 8 equals 0 plus 8. Right, so these are going to add each other out to give 0. So we're left with 2y plus x equals 8, sharp. Now we're going to solve for y, but before we get there, 2y plus x, or rather let me write it so that it's almost underneath each other. 2y plus x minus x equals 8 minus x, and this is minus x on both sides, and these two steps are just simply making use of the additive inverse rule. That's all there is to it, right? So don't panic. So those give us 0, so we're left with 2y equals negative x plus 8. I just swapped these two around. This is very much the same thing as that. They're commutative because there's no multiplication or division. It's just addition. Taking one to the front makes it negative, but the other one without a sign is just implied that it's a positive sign. Sharp. Wait, what?
No, sorry, that's not wrong.
Oh, okay. So we're gonna then divide by 2. So when we divide by 2, we're using a multiplicative inverse, and we divide right through by x, by that 2, and that leaves us only with y equals negative a half x plus 4. Right? And when you pay close attention, this is in the form y equals mx plus c, where m is our gradient, x is our independent variable, and c is our y-intercept, right? So now on page 848, what they automatically conclude is that therefore the gradient, which is change in y over change in x, equals -1/2. And remember our definition of gradient. It's change in the vertical distance divided by change in the horizontal distance. So it's how high am I going compared to how far across am I going. And the simple example is a wheelchair ramp. It has a gentle slope because how high you go is much shorter than how long you go, making it easy to access that with a wheelchair ramp or if you're on crutches. But if you're hiking on an ancient path in the Aztec mountains there, Machu Picchu, the staircase looks like you could easily slide and fall immediately. Then how high you move is much greater than how far across you move. So in other words, it's a very uncomfortable steep slope where the change in the vertical direction is much more than the change in the horizontal direction for ascending that gradient, that slope. And our gradient is that -1/2, and in other words, it's descending, so it's not going up, it's instead going in that direction because our change in y in relation to change in x is negative. So when it's negative, our graph has a line that slides from the left to right in the, like it slides down. But if m is positive, then from left to right it slides up. Now c in this case equals just 4, and c is this part over here. It's called the y-intercept. Y-intercept, right? So where there is an intersection of the line, the straight line y equals mx plus c, and the y-axis, that is called your y-intercept, right? Now that terminology is very important for the simple reason you will often get asked to code the significant characteristics of a graph, and such data needs to be made clear, needs to be communicated clearly as possible, right? So now we have to draw the graph. So step 2, we draw our graph. Now when we draw our graph, we know that we have a y-intercept of 4. So we'll start off first by drawing our coordinate axis system with x on the horizontal axis and y on the vertical axis. And to indicate that we are familiar more or less with what it is we have to do, I'll start off by saying maybe the highest point on our y-axis can be 5. So we'll start there, 1, 2, 3, let me make it a bit lower, 3, 4, and then that's a bit high, 5, so maybe 6, maybe 7, sharp. And then we can do the same, -1, -2, -3, -4. But we'll just stop there, right? -x, -y, right? Then on the x-axis we can do similar, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'll just stop at 10. Then we can go the other way. -1, -2, -3, -4. I'll stop there, right? So now our y-intercept is 4. And the important thing to note with the y-intercept is that if you are just told that the y-intercept is 4, then we know that the value of x there is 0. So it's also correct is 0. Why is it 0? Because where x is 0, we're looking at numbers on the y-axis. And if the y-intercept is 4, then what this simply tells us that where x is 0, y is 4. So I'll just erase that so there's no confusion. I want the blue point to denote that y-intercept. And now the next point is so our y-intercept we find by making x equal 0 for y-intercept, right? Now when we make y equals 0, or rather x equals 0, then we have y equals half x plus 4 becomes y equals a half times 0 plus 4. And a half times 0 is 0, and that just gives us 4. And if we want, and this just gives us the y coordinate. And if we want the x coordinate, we simply substitute where y equals 4, how much is x? So we can put there y equals, so for x coordinate we can have where y equals 4, what's x? Plus 4. If we do additive inverses, -4, -4, that gives us 0, then we have 0 there, then 0 equals a half x, and x is 0. Yeah, so then this gives us x coordinate of y-intercept, right? And that's just that point there. So that one is clear, right? That's how we find the coordinates for C.
Yeah.
Sharp. And now we must find the x-intercept, and that's the point where y is 0, so it's there, where y is 0, and we need to find what x is. So x-intercept is where y is 0, but we'll start by finding x-intercept by making y equals 0 such that a half x plus 4 equals 0. We do additive inverses, so -4 equals -a half x. We do multiplicative inverses, therefore x equals 8. Are you clear on the math on this one, or should I add and show them addition and division and multiplication?
Yeah, I'm still with you.
Yeah, I'm asking for this part here. Should I illustrate the math by showing overtly the additive and multiplicative inverses, or can we just carry on? Everything is clear. We can carry on. Okay, wonderful. Right. So now we've got the second point, which is the x-intercept, which is the point 8 is to 0, right? And how do we find that y is 0 there? We simply make, in the equation, y equals a half x plus 4. We simply make x equal 8. And if we substitute 8 there, we get -a half times 8, which is 4, which is -4 rather, plus 4, and that gives us 0. So indeed, our graph moves something like this. So we'll have a line, and that graph, we finish off by writing the actual relationship, the function, the rule, minus a half x plus 8. My mistake, plus 4. Right? And then the second thing, now that we have the coordinates of the x and y intercepts, we can also find out the gradient. And the gradient is change in y over change in x. And what that means is that you have the values for y2. So you can make this x2, y2, x1, y1. Or you can have these as x1, y1, x2, y2. It really doesn't matter, it's up to you. Whatever the convention you choose there, you stick with it down here, where I'm writing x2 and x1. Because when you don't stick with it and you swap things in between, you'll get errors that you're prone to get, just as if you change convention in the middle of a calculation for, say, physics, or when you choose the direction, etc. Right, so if we take the first convention where y2 is 4, then y1 would be 0, and x2 would be 0, and x1 would be 8. And what this gives us is 4 over negative 8, which is 4 goes there once and goes there twice, which is negative a half. That corresponds with our conclusion that m is negative a half. So, that being said, we now come to a conclusion of significant. Let me not write here, let me not be lazy and open a new page. So now, therefore, significant characteristics of this graph, characteristics of y equals negative a half x plus 4 are that, number 1, the gradient is negative a half. The gradient is negative a half because every time the graph goes down once, right? We go down 1, 2, 3. We go across twice and we land somewhere there. If we go across twice from 2 to 4, then the corresponding y value is 2. Now if we go down the graph, if we go across from 4 to 6 twice, then to get to the next y value means we'll have to go down once. Each of those points are on the straight line. The points 2 is to 3, the points 4 is to 2, the points 6 is to 1. Each of these points are on the straight line, and even if you substitute these into that straight line, you will get that the math does add up and it is correct. So that being said, our gradient is indeed a half, negative a half. The second thing that we must point out that is significant characteristics are the y-intercept. So y-intercept you can just declare on your paper when you're answering. Y-intercept is 0, 4, and x-intercept is 8, 0. 3, the domain, right? Now the domain is our description of this x values that are involved in this relationship, right? Now the x values are simply real numbers. I don't want to make it too complicated. I think you're still new to this, so I'll just be direct with it. And this is on slide 9, right? It's on slide 9, not cloud 9. It's x is a real number. And I'm going to explain that using the very same graph that we've got, right? On our graph, which looks something like this. Maybe not that. Maybe something like that. Nope. Maybe something like nope. Nope. Maybe something like that. I fucks with that. Alright, cool. Right. When we look at the x values, right? These values here on the straight line, right? Like, you don't need to make it complicated. It's pretty straightforward. We don't need to make it complicated. It's very straightforward, right? When we look at the numbers on the x-axis, just the numbers here, right, on the x-axis for that graph, right? The x values there, they include 1, they include 2, they include 1.5, they include 2.5, they include 3.5, they include square root of square root of 2, they include square root of 3, they include square root of 5. And I'm mentioning these numbers intentionally because these are natural numbers, whole numbers, integers, and irrational numbers. But all of these are real numbers, right? And our straight line can go, like, x can go infinitely in this direction, just as x can go infinitely in the positive x direction. Regardless of that, right, our y function, the blue function, will always decrease from positive y to negative y. But its action of decreasing does not change the fact that even the y values are real numbers. That one doesn't change that. yeah, let's just wrap up in the next 5-10 minutes. Let's finish up. Let's wrap up. Right. So I was saying, for any value of x on the x-axis, right? It can be negative times the square root of 2. It can be negative times the square root of 3. It can be positive times the square root of 2. It can be for any value of x, right? X is a real number. Whether it's a square root of something, irrational number, whole number, natural number, but it's a real number, right? And whatever value of x you get, when you substitute into our rule there, any x value that you substitute into our rule there, it will give us a number for y. Now, whatever the value of x is, doesn't change the fact that this rule, y equals negative a half x plus 4, this particular rule gives y a decreasing tendency. So y tends to change from being positive above the x-axis to being negative below the x-axis. So it is decreasing, right? But even though it is decreasing, any value of y from positive, whatever it is up there, to what it will be down there, negative whatever it will be down there, any value of y there will also be a real number. And that's what these two things mean, domain and range. And remember, when I started on the 6th slide of today's class, when I started, I spoke about domains and ranges, right? On that slide. Yeah. Domains and ranges. Sharp. I think we went a bit more into depth on slide 6. So now about that, right? The domain of a function tells us more or less about the behavior of the x values. And the range of a function tells us more or less about the behavior of the y values. So in this instance of our this particular straight line that we are solving, the behavior of the x values is that the x values, whether looking towards the right, to the left, or to the right, whether we're looking at the behavior of the x values to the left or to the right, thank you DJ Cleo for the hits, that behavior shows us that x values are real values. And even if we substitute any value for x and get a corresponding y value, even the y values are also real numbers. So we're gonna end the class here. ER.
Real number.
Okay, so this symbol means element, right? This R means real number, denotes real number. These are just curly brackets, the one that look like this. I was just lazy too. That one. And this sign here, we say such that, right? Now this R is real numbers, and natural numbers are this, whole numbers are this, there's a subscript 0, integers are this, that one, do you see? Yeah, so this is notation for math that we use in sets. You see, like this set that I was showing you here, this pair of sets that I was showing you here. Where is it? Where are they? These ones here. right? When you're analyzing sets, Venn diagrams, etc., etc., this notation is what we use. So there's different symbols. There's quite a number of symbols. I know you can also look at the union. You can also look at the intersection. Yeah, what? So this would be union. This would be intersection. So it's all different types of notation for discussing types of sets, and it's also quite useful for discussing functions. Anything else you want to ask?
No, that's it. Thank you.
All right. So for today's class, I just want to ask you, how do you feel about us starting with the summary of what we're going to do and then starting with it as we go?
Good.
All right,
It's
cool.
like a preamble.
Like a preamble. I like that. Then we don't dive into a chapter unaware of what's going on. I like that. So you have access to these notes. So if you feel today you've got time or sometime during the week you've got time for self-study, by all means, just brush through these. I'm uploading the videos by one, so I'm just a bit behind. I think I was nursing signs of creeping burnout, if I'm being honest, because I was